Describe and discuss a suitable system together with the corresponding boundary and surroundings for each of the following devices: a domestic hot water tank fitted with an electric immersion heater, a steam turbine driving a generator in a power station, a single-cylinder four-stroke petrol engine, in each case, how is heat and work transferred? Okay, so the first question is, how do we define a system in order to do analysis of a hot water tank? Right, so let's just draw what the system might look like, or perhaps, of course, try it yourself first. So we can imagine a large tank, partially filled with water. There's an electric heating element in the tank. Maybe there's a water inlet and a water outlet. Okay, and perhaps there's a lid. It could be closed up here and then open, just inflow and outflow of water. So how can we define a system here? In order to define the system, we need to specify the boundary of the system. Now, we have a lot of choices here. We could make the system very large to include all the materials of the tank and its insulation, and then we'd have perhaps might complicate some of our heat transfer calculations. We could have it just to include the inner surface of the tank, so that would include some air and some water and the metal, so it would be we'd have this phase transition between gas and liquid here. What I think is maybe in some ways the simplest system we could define would be to define it along the boundary of the tank, along the interface of the water and the air, have it cut across the inlet pipes, and then perhaps for it just to follow the metal surface of the heating element, and that way it's a single component mixture of pure water. That makes the thermodynamic analysis a lot simpler. We just need to know a few parameters about it, like how much mass there is, what its temperature is, what its pressure is. So that would make it simpler. Now, how is heat and work transferred in this system that we've now defined? Well, this heating element's receiving electrical power and being heated by electrical resistance, so it's going to be hotter than the water potentially. Heat will be conducted away or from the surface of the heating element into the water, and then can be transferred through the liquid by convection and further conduction. What else? We can have heat losses to the walls of the tank. Of course, we'd want to insulate the tank. So if we're pumping water into the system, that kinetic energy could be dissipated in here and cause a further heating of the system. So this water inlet outlet is potentially a source of work input. So the next system we're going to consider is a steam plant. Now, you haven't seen steam plant in the first year of your course, so we'll just explain what the different components are. The objective is to push steam through a turbine, high pressure steam in one end, driving a metal blades around and round, and as the pressure drops. So we draw a turbine schematically like this, because it's an expansion process. Steam comes in at high pressure here, and high or low specific volume leaves at low pressure, high specific volume here. So it expands as it goes through. And this steam turns the turbine and drives a shaft, and that presumably drives an electrical generator over here. This low pressure, colder steam comes out and goes into what we call a condenser, where it's turned back into water. This water goes into a pump to return it to the original pressure, but it's only pressurizing water now, so it's costs less energy. And we put the water into a furnace or into a boiler, gets turned back into steam, and so we should maybe put an arrow on here so you know the direction of flow. So that's the cycle. So it's a closed cycle, so we can define a closed system here. Let's just label this. So this is turbine. That's the boiler, and we call this the condenser. So let's draw a boundary around here, so we don't draw it too close to the system where we get tangled up in the actual geometry of the heat exchangers and the turbine blades. We just draw an all-encompassing control surface on the outside. But there are various things going through this surface. So here we have this shaft work leaving the control volume, control surface. Here we have work going into the system to pressurize the water. This condenser is as the steam gets converted back into water, it's rejecting heat, so we have heat going out there. Of course, if we were to apply the first law sign convention, this arrow would go in the other direction, and Q would be a negative value. Here we have a furnace heating the water to convert into steam, so we have heat input there. So we have these two heat exchangers and two work exchangers. Now the third example is a petrol engine. Again, pause the video and have a go on your own. But just to sketch what a piston engine looks like. So these are the valve ports, and this is the cylinder block. This is the exhaust. Intake, valve, and a valve. So this is all metal. You have a piston that's going up and down here. And a crank down here. So just think to yourself, where should we draw where is it convenient to draw the system boundary? Because we can draw it in a number of places. We could draw it, again, an all-encompassing one, but that would mean that we had to deal with many different materials, the metal, the valve materials, different moving parts. It would be very complicated if we drew the control surface on the outside. So what I suggest might be useful to do is to have a system that just contains gas, and you could do that by having the system boundary go along the inside of the metal here to cut across the valve ports here. And now the piston is moving, but we could have a moving control system or control surface. So we'll just draw it along the surface of the piston metal. So now we have an only gas system. When the valves are open, it's an open system. It's exchanging mass. So what are the heat and work flows in this case? Well, if the combustion products are hot, or hotter than the metal, there'll be heat flux into the metal. So that's a heat exchange. Now, is there a heat input? Well, strictly there is not a heat input to a combustion engine like this. There's an input of chemical fuel energy. So actually chemical energy gets convected into this system when the intake port is open, and the fuel air mixture is inducted. And one of the major transfers of energy or heat energy is actually the convective flow of heat out of the exhaust port when that valve is open. In terms of work, the control surface, or the control, our system that's contained by this blue control surface, does work against the piston as the piston moves up and down and the system changes volume. So that's how we do useful work. There's also some work done by sucking and pushing the mixture in and out of the system. So, just to conclude, how we define our system boundary really can influence how difficult it is to do the analysis. So we need to think a little bit carefully about how we set up the boundary.